And now we have a couple of easy corollaries of the Gram Schmidt procedure, or corollaries if you're feeling British. So it turns out that the Gram Schmidt procedure is actually more of a theoretical tool than something that's actually computational. So one of the main applications is just to use it to point out that every finite dimensional inner space has an orthonormal basis. So just the basic existence result. And so this is super straightforward because it's just combining some things we've already seen. So we know that every finite dimensional vector space has a basis. And that's more or less by our definition of finite dimensional vector space. And then the Gram Schmidt procedure converts this to an orthonormal basis. The end. So not much to that one. And then we also have the idea that every orthonormal list can be extended to an orthonormal basis. So this is just sort of the orthonormal upgrade of the corresponding result from chapter 2b or whatever. So every orthonormal list extends to an orthonormal basis. And so let's see. So if we have an orthonormal list, let's go up to EM. So if E1 through EM is orthonormal, then we saw earlier that an orthonormal list is independent. So it's independent. And we know that any independent list extends to a basis. So we'll call that basis E1 to EM, V1 to V N. Okay, so then if we apply the Gram Schmidt procedure to this, then let's see, so we'll get U1 up through UM plus 1 up through UM plus N. All right. But then if you look at the definition of the basis from the Gram Schmidt procedure, Uj is going to equal Ej. Because, let's see, well, clearly U1 is going to be the normalization of E1, but since E1 comes from an orthonormal basis, it's already a normal vector, so U1 equals E1. And then what do you do with U2? Well, you subtract off the projection to E1, but the E's are orthogonal, so there is no projection to subtract off. So U2 is just the normalization of E2, which is already normal, so it's just E2. And continue. So that's it. We're done.